Yes. Yes. Go get this. Now, I've told you to go get these things before when I go through them, but you really, really, really have to go get this because that data up here, I'm going to be using, and I'm not going to go ahead and write that all down on the board. I'm not going to reinvent the wheel. It's on the sheet. Go get it. You're going to need it to solve this first problem. If you don't have it, you're going to not know what I'm doing and where I get these numbers from. So please go get that. And I'm not going to write it down because you can go get it, okay? Eat your popcorn, drink your root beer, but go get this sheet so we can go through this data. This first problem here is going to determine what's called a rate law. Now, a rate law, what's that? Sounds like an equation. It is. A rate law is an equation that determines at what rate are reactants being used and products are being formed. And those rate laws, well, usually most laws in chemistry, like Boyle's law and Charles's law, and they all have set equations. Well, this is going to have a semi-set equation. Because every rate law is different. Well, that doesn't make it a law then. Laws are supposed to be the same. Well, rates will change with different amounts of stuff and temperature of stuff. And you know this is true. Yes, you do. Yes, you do. You know this. I'm going to bring out some chemistry that you already know. You know that rates of reactions happen faster when they get higher temperature. You know that. Think about this. Take a gallon of milk. You just go ahead and buy 2 gallons, 2 gallons of milk, okay? And take 1 gallon, okay, and put one in the refrigerator, okay, and leave it there. Take the other gallon and put it outside. Now, it's pretty warm out today. It's going to be like mid-80s. Leave it outside in the sun in 85-degree temperature. Okay, come back, I don't know, 6 hours later. Drink the one from the refrigerator. Ooh, so tasty and good. Then go ahead. Drink the one that's been in the sun for 6 hours. You just know. You're not going to do that. You know that. You know it's probably spoiled, or at least beginning to spoil at this point. It's going to be spoiled. You know that. See, you know about rates of reactions when it comes to temperature. You know that reactions happen faster. Of course, that reaction in milk is going to be a bacteria-based reaction, but it's a chemical reaction. You're changing the milk. It's a chemical change. So you know that. You know that things go much faster when it gets really warm. All right, and when things get cold, reactions slow down. This is why you put things in the refrigerator. They'll last longer. See, you know chemistry. You do. Now, typically, actually, there's kind of a general rule, I wouldn't call it a rule, a guideline, a general guideline as to reaction rates for every 10 degrees Celsius increase. I'll put kind of equal to, it's not written in stone here, it depends on the chemical reaction. But for every 10 degrees Celsius increase in temperature, you will typically double the reaction rate. Yeah, you'll double the reaction rate. So let's say your refrigerator is at like 35 degrees Celsius, you know, nice and cold. And your temperature, and these are degrees Celsius. Oh no, 35 degrees Celsius would be really hot. 35 degrees Fahrenheit. So let's say about 2 degrees Celsius, okay, just above the freezing point, keeping things nice and cold. And outside it's 32 degrees Celsius. That would be a hot day. That'd be like 90 degrees. Nice summer day. Well, let's see. 2 degrees Celsius, 32 degrees Celsius. Every 10 degrees that you go up, you double the reaction. So, let's see, 2 degrees to 12 degrees, double it. 12 degrees to 22 degrees, double it again. And then 22 degrees to 32 degrees, double it again. Double it, double it, double it. 2 times 2 is 4, times 2 is 8. So your milk, you would expect to spoil about 8 times as fast outside than inside. All right, okay, yeah, and it's typically what happens. So it's a typical general guideline of reaction rates. And you know that. You know that's true. What else do you know? You also would know, I think you know this, that the more stuff that you have in solution, the faster reactions will happen. If you dump in more acid, the reaction goes crazy, right? Because you have more acid there. The more stuff that you have, the faster reactions will take place. And I'll just do a little drawing for you. Just use your imagination here. That let's say that we have a container, a beaker of water, and in it we put compound A, or maybe it's element A, whatever. It's chemical A, and I'll call it chemical A. Okay, that'll be my black marker, and chemical B equals my red marker. Okay, I'll say I got 5 particles of each one of those. For a reaction to happen, these things got to crash into each other. They have to smash into each other. Well, if I only have 5 particles of each one, what are the odds that anything's going to be smashing into something else in the next second? Probably not very good. But let's say that I crank up okay, I put 10 more particles in, so I've tripled the amount of compound B or element B. Then what I have is a lot more particles. What are the chances now that I'll get a collision in the next second between A and B? Pretty good. And if I bump up the amount of A, even better. So the concentration, the amount that you have, is also going to determine how fast reactions happen. Reactions can't happen unless things bump into each other. They got to bump, stick, do their thing. And if they're not bumping, you're not reacting. So the more stuff, the more bumps, the better we have, the faster we'll have our reaction rate take place. All right, the reaction rate. So now we know 2 things that affect reaction rates. We know that temperature is going to do it. Increase temperature, increase rate of reaction. We know the concentration is going to do it. Increase the amount of particles in your solution, then you're going to have faster rate of reaction because they're going to bump into each other. This is actually all called collision theory. What I'm talking about here is called collision theory. So collision theory, when it comes to reactions in chemistry, you have to have things collide in order for them to interact. So collisions, it's all about whackage. Whack, whack, whack. It's all about whacking into things. That's what it's about, Charlie Brown. And you're going to have faster moving particles at higher temperature. Faster moving particles, more chance of a collision per second. If you have more stuff, more chances of collision per second. So those 2 things, increase concentration, increase temperature, increase the amount of collisions, and the collision. Now, every time something collides doesn't mean it's going to react. They have to collide with, if they collide with too much energy, too fast, there's no time. So there's some things that kind of go into collision theory, and they also have to react in the right way. If they're not oriented correctly, then they might not react. As a matter of fact, most collisions do not result in a reaction. Most don't. But of course, the more collisions you have, even if you have a low chance of reaction, the more reactions you will get. Okay, so I'm doing a lot of theory babbling here. Let's take a look at this first problem. And this first problem here has some data. And that data we have to use to solve this right here. Determine, okay, I can't read it here backwards. Determine the rate law. So we're going to determine the rate law. And these rate laws, I'll give you the general form for a rate law. This is the general form for a rate law. How fast reactions happen or how fast chemicals are used up or made. So the rate of a reaction, okay, the rate of reaction, how fast something gets used or made, is going to be equal to K. I use little k. That means a constant, remember, from the colligative properties. A constant. There's something called a rate constant. And we're going to put in square brackets. Why square brackets? Square brackets mean concentration. They mean concentration. You see square brackets, that's a concentration, like a 2 molar or a 3 molar concentration. So square brackets, not these brackets, those don't mean concentration. That means you're just going to multiply some number. And I'm going to put here A for chemical A, B for chemical B, because these can be different reactions, well, different A's and B's, right? Makes sense. And up here, for the superscripts, I'm going to put X and Y. Well, why did you do that? Why did you put an X and a Y up there? It's kind of high up there. Can you see that? Okay, X and Y, you can see that. Yeah, okay. because they're variables. They can be different. There can be a 0 up there, could be a 1, could be a 2, could be a 3. Okay, and so those are different. Well, if these can change and those can change, it doesn't sound like a very good law because it's always changing and those are not what laws do. Okay, yes, that's absolutely true. But the laws apply to certain chemicals and their concentrations at certain temperatures. So this K value is going to be dependent upon what temperature it is. So if something is at 1500 degrees, as opposed to 10 degrees Celsius, that K value is going to be different at 1500 degrees. Because remember, that's your multiplier for how fast these happen. So if this K is representing 1500 degrees, it's going to be different than 10 because this reaction is going to take place much, much faster. And the rate will happen much faster. So the rate law is dependent upon temperature. This is going to be dependent upon temperature, my K value, and upon concentrations. Those are what those brackets, square brackets mean. Now from this data, for first problem, we're going to figure out the rate law for this particular reaction. Every reaction has a different equation. And we can only figure out the rate law by looking at data. That's why you got to have your data. Go get your data. I'm not going to write this whole thing on the board. You should have it in front of you. So this data is going to provide me with my rate law. You can't get a rate law without experimentation to show data through experiments. Okay, you got to have those. Here we have experiment 1, 2, and 3. And we have data for the 2 reactants. Now, let's write the equation down. We got 2 nitrogen monoxide plus 2 diatomic hydrogen makes 1 N2. This is balanced. So if you don't believe me, go ahead and try it in 2 waters. So there's my reaction. Okay. Well, can I get a rate law from the coefficients? Because you use coefficients to figure out the rates of how much stuff is going to be decreased and increased in the last problem. If I were given a rate of any of these, I could then figure out the rate at which things increase or decrease for each individual part. But I would not be able to get a rate law for this reaction. The rate law for this reaction can only be determined by experimental data. We have to use experimental data. Yeah, we do. Okay, all right, well, how do I do it? All right, check it out. Okay, what we do is we take the data and we look at, we're going to look at experiment 1 and experiment 2. We're going to compare the rate change of, and this is the rate change, these are the concentrations. This is a concentration, right? Concentration of the nitrogen monoxide. And here's the concentration of the hydrogen. And let's check between experiment 1 and 2 the change in the concentrations and what effect they had on the rates. So if you look over here on the left, these are the concentrations of, here's my nitrogen monoxide and here's the hydrogen. And it's all about the reactants. These, and that's the other thing too. These, I don't know if I mentioned this, the A and the B are only the reactants. Because it's the reactants that determine how fast the reaction happens. So in the rate law, you're only going to have the concentrations of the reactants. Okay? Because they determine, the reactants determine how fast stuff gets made. Okay, so these determine the rate. And these are telling me that in experiment 1, I have 5.0 times 10 to the minus third of the nitrogen monoxide. Then, in experiment 2, I have 10 times 10 to the negative third. What happened? What did we do from experiment 1 to experiment 2? What did we do to the nitrogen monoxide? We doubled it. Experiment 1 to 2. From experiment 1 to experiment 2, we doubled the amount of nitrogen monoxide. What did we do to the hydrogen? Check it out. We kept the hydrogen the same. We kept it from 2 to 2. That's called control in an experiment, people. That's control. So we didn't change, we didn't scooch with this one. We're checking out what happens to the rate of the reaction, how much product we form by scooching with one thing at a time. If you mess with both, then you don't know what was causing what. You don't know that, it's not controlled. So in the experiment 1 to 2, we didn't change that, we left that alone. All right, okay, you see that, right? We doubled this one. Experiment 1 to 2, but we left this one alone. Look over in the third column. What happened to the rate of the reaction? That's the third column. What happened to the rate? Okay, the initial rate of the reaction here, okay, look at those numbers. The initial rate in experiment 1 was 1.3 times 10 to the negative 5. In experiment 2, it went to 5 times 10 to the negative 5. So we jumped in this initial rate from 1 times 10 to the negative 5, 1.3 to 5 times 10 to the negative 5. All right, so what does that mean? What does that mean? Now, the times 10 to the negative 5 is the same, right? Blah, blah, times 10 to the negative 5, blah, blah, times 10 to the negative 5. It's the same. So that's not what we're going to look at. Look at the two numbers at the beginning, 1.3 and 5. Check that out. So experiment 1, 1.3. Experiment 2 was 5. How many times faster? You can see that this is going faster, right? The rate's higher. That's a rate, so it's faster. So how many times faster? From experiment 1 to experiment 2, our rate jumped by how many times? That's what we need to look at. How many times? I don't know. How are we going to get that? Well, let's take 5 and divide it by 1.3, and I get 3.85. 3.85 times is fast. Now, I've told you before that experimental data sometimes can come out to be a little bit skewed because, it's an experiment. Not everything's perfect. That rate change should be a whole number. 3.85 times is fast. What whole number do you think that should be? 4. So this is a 4-fold or a 4-time increase. A 4-time increase. We went from 1.3 to 5. That is 3.85, but 4 times as fast. This is about 4 times as fast as that when we doubled the concentration of nitrogen monoxide. Okay, now here's what we're going to do. Our rate law is going to contain the 2 reactants. So we've got to put those in. So let's go ahead and do that. And I'm still answering. This takes a lot of explanation. This does. It takes a lot of explanation. It just does. It's not easy. I never promised you a rose garden. No, I did not. So this is a little hard, but we can do this together. I have faith in us. Okay, the rate law for this reaction at this temperature, and this is at a particular temperature, I'm sure it was given there at 1280 degrees Celsius. That's a real hot day. All right. So this, K, and we don't know what that is yet. We don't know what that is. It wasn't given in the problem. We don't know what that is. In fact, that's the next part. We have to figure out what that is. But for now, we don't know it. So what is K? A is nitrogen monoxide. Okay. And B is the hydrogen. Okay, so I got that. Okay, we just put the reactants in for A and B. Okay, put them in those square brackets. Those are concentrations. Okay, I need to put a superscript here and a superscript here. What do I put here? All right, that's it. That's it. If you look at the data, and for the nitrogen monoxide, we see that by doubling the nitrogen, you can't see that, by doubling the nitrogen monoxide, we quadrupled, and that means 4 times. We raised the reaction rate by 4. That's called a squared relationship. That's called a squared relationship. Okay, I hope that you're watching this video. And I hope that when I give you a problem like this, and I will give you a problem that shows data. I'll give you a data table just like this, set up the same, 3 experiments. And when I have one that potentially will be 4 times the increase, you will remember that means a squared relationship. So I don't get it. What do you mean? Okay, here. 2 times the concentration, we double the concentration. If we square 2, what do you get? You get a 4-fold increase, people. So that is by doubling the concentration, if you get a 4 times increase in reaction rate, that is a squared relationship. That means that that exponent that's going to go right here, this exponent is going to be a 2. Now, that might not sink in the first time that I've gone over it with several of you. You need to rewind and go through it again. I'll say it one more time here, that if we double the concentration of a reactant and we get a 4-time increase, and 3.85 it rounds to 4. It's going to be pretty close to, you're going to be able to see that reaction. Then that means we have put a square. Well, that's a squared relationship. I put a square up here for my superscript. We need a exponent for the hydrogen. Let's do it. Let's look and see what the data says for the hydrogen. Okay, for the hydrogen, we kept it the same for trials 1 and 2. We didn't change it, that's control. For trials 2 and 3, we changed the hydrogen, but look what we did. We kept the nitrogen monoxide the same. The control is between experiments 2 and 3, we left this one the same, but we doubled the hydrogen. Okay, so we went with the hydrogen from 2 to 4. You see that? Okay. So when we went with the hydrogen from 2 to 4, we doubled that one. What happened to the reaction rate? It went from 5 to 10. 5 to 10. Now the times 10 to the negative 5 is no different, but look at the number in front, 5 to 10. It doubled. So when we doubled the hydrogen, we doubled the reaction rate. That's a direct relationship. That exponent, when you double and you double, is a 1. So the hydrogen gets a 1. Now technically you don't have to write it. When it's a 1, you can just leave it alone and not write it. So I'm not going to, because typically that's what it would be. You wouldn't put the 1 in. So when we doubled the hydrogen concentration between experiment 2 and 3, we doubled the reaction rate. When you double and something else doubles, that's called a direct relation. The first time we had a squared relationship with the nitrogen monoxide doubling it. That's a squared relationship. When you double and you quadruple, squared, double and double, direct. Direct means your exponent's a 1. So if I were to double this H, my reaction rate would double, just like it did in the experiment. If I doubled the NO, you have to double it and then square it 4 times the rate. So that's my rate law for this reaction at this temperature. All of that for just part A of this video. Oh my goodness. I don't like videos really that go 21, 22, 23 minutes. But sorry, this one just is. It just takes a long time to get through this. Okay, so what we will do is write that down over here. Our rate law for this reaction equals K NO squared H2 single. That's my rate law. Okay, I'm going to get rid of this. Actually, I don't need this anymore. I don't need that anymore. I have my rate law. I'm good to go. Let's figure this out. I want to get this done. Video's getting long here. B. Let's do part B. Stick with me here. I know. Go get some coffee. Slap yourself in the face. Come on. You can do this. We can do this. B. Determine the rate constant. Ooh, we got to figure out the rate constant. We got to figure this out. We got to figure K out. K. It's funny. K. Solve for K. K is going to be equal to rate divided by the concentration of the nitrogen monoxide and the hydrogen. K is equal to rate divided by these two. Pull these two down, that's what we get. There's your setup. I need this. I need the rate, I need nitrogen monoxide concentration, I need the hydrogen concentration. Well, you have that. You have that 3 times. So you have 3 choices here. There are 3 choices Experiment 1, Experiment 2, Experiment 3. You got the concentrations and the rate. Which one do I use? Which one do I use? Any one you want. It doesn't matter. No matter which experiment, 1, 2, or 3 data you choose, you're going to end up with the same answer for the K. Because remember, it's a constant. It's a constant. So it doesn't make any difference what data I use. It's going to end up with the same constant because that's what constants are. They're the same. So just pick one. Angsty Billy, what do you want to do?
Now I'm going to put experiment 3 data.
Okay, Angsty Billy, we'll go with experiment 3 data. Okay, so in experiment 3, the concentration of the nitrogen monoxide, okay, I put that in the bottom. So let's see, let's go over here. K equals the rate. Now the rate for experiment 3 is 10 times 10 to the negative 5. 10 times 10 to the negative 5. Let's see, I just put that out of scientific notation. 1, 2, 3, 4, 5. So I moved it 10 times 10 to the negative 5. 1, 2, 3, 4, 5. Okay. You can keep it in scientific notation if you want. You want to put 10 times 10 to the negative 5 up there. Go ahead. That's the same thing. Same thing. On the bottom, I'll put the concentration of the nitrogen monoxide from experiment 3. We got to be consistent. We got to use all the same experiment data. Okay, so the concentration is 10 to the negative third for the nitrogen monoxide. So 10 to the negative third is 0.010. Okay, 1, 2, 3. Again, you can leave that in scientific notation if you want. Squared, don't forget, we got to square that. The nitrogen monoxide was squared. Okay, then what? We need the concentration of the hydrogen for experiment 3. 4 times 10 to the negative third, 0.004. Okay, 1, 2, 3. All right, that's it. There's my setup. I'm going to do the math, and we're going to get that K value. You could do this with a different set of experimental data. Do it. Don't believe me. Don't trust me. Try it with experiment data 1. Try it with experiment data 2. See what you get. All right, see what you get. Let's see. Okay. So 0.01 squared. Okay, it's 1 to 10 negative 4. Okay, so here we go. 0.00010. Okay, divided by 0.0001. Okay, enter. And then, like the 0.0001 is this squared. I gotta remember to square that number and divide that into this and then divide that into that. Or you can multiply these together first and then divide those in, either way. And then we'll divide by 0.004. And I get 250. 250. 250. Don't worry about the units. And here's why I say that. The units are going to be different for every problem. Because sometimes you're squaring the concentration, sometimes you're not. So they end up, and sometimes you're quadrupling it. So they're always different. Look, if you can get the number answer, I'm happy. If you can get that, I am happy. So just get the number answer. And for every one of these problems, it is a different K value. This is the longest video that I have ever made. Okay, we're going on a record here. And if you're still with me, you're a good trooper. Yes, you are. Yes, you are. Okay, we're almost done. So 250, that's our answer. Determine the rate of the reaction when the concentrations are blah, 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 and blah, blah, blah. Here's our equation. We have our equation for this reaction at this temperature set. Okay, we have this rate. It wants to know that, so all I need to do is plug in for these, and I have that data. They told me the concentrations are these. Let's put those in, solve for rate, and get this problem done. Okay, we just figured out K. We just figured it out. So from part B, we got to use it in part C. So this is 250. It doesn't matter what concentrations I throw in there. At this temperature, that's the rate of the reaction. That's what it is. It's a constant. Okay, that I got to throw in there. What do we give me for the nitrogen? 12 times 10 to the third. That's 0.012. At this point, I'm not going to put the square brackets because when I do math, I just use the round brackets. So round bracket it. Okay, that's 3. 1, 2, 3. Yep. Square it. Don't forget to square it. And then the hydrogen concentration, we put that in. And that's 6 times 10 to the negative third, 0.006. We do the math on this, and we'll have the rate of this reaction at this temperature with these concentrations. Okay, so 0.012 times 0.012 times 0.006 times 250. Finally, the rate of this reaction is going to be equal to 2.16. That's the answer, times 10 to the negative fourth. Or you could write it out. Okay. 0.000216. 1, 2, 3, 4. And the units for a rate, the units for the rate constant are always all over the place. It can be anything, but with a rate, the units are always molar per second. Guys, I'll put molar per second. So molar per second, molar per second. Those are the same answer. You check our answers, and I put 2.2 times 10 to the negative fourth. Same thing. This one ran over a half hour. It's a long problem. And when you do one of these, and you will have one of these on a test, make sure that you've gone through it. There's going to be a whole bunch of points here available for you. You don't want to give those points up. Okay, I know. Finally, I need lunch. I do.